So let me give you some examples of uniform and non-uniform convergence. I hope you know the definition. So I'm not stating the definition of uniform convergence. Okay. I'll first state the definition of uniform convergence, and then I'll start with this. So uniform convergence of sequence of functions. So what is the uniform convergence of sequence of functions? Let this be a sequence of functions on the domain D subset of R. Then Fn is said to be uniformly convergent to a function f on D if, so this is the definition, if for each epsilon positive there exists a natural number m depending only on epsilon. This is important. Depending only on epsilon such that modulus of fnx minus fx is less than epsilon for all x in the domain. And I should write this for all. Firstly, I should write for all n greater or equals to n, and for all x in domain. So what is the thing? Whenever you can find this natural number m depending only on epsilon, not on the point that you are choosing. Okay. So this I have to prove uniform convergence. I have to prove that this natural number m depends only on epsilon, not on the point that you are choosing. Okay, so this is the definition. So let me take some examples of uniform convergence. So this is the first example. Show that the sequence f of xn where f of xn is x to the power n is uniformly convergent on this subinterval 0 to k, where k is strictly less than 1. Okay, definitely k should be greater than 0, but not uniformly convergent on 0 to 1. Okay, so x to the power n, this sequence of function, you have to prove that this is uniformly convergent on 0 to k, where k is strictly less than 1. That means if you take any proper subset of this subinterval, this will be uniformly convergent on this subinterval. This will be uniformly convergent on this subinterval. But when you include 1 in your interval, that will no more be uniformly convergent. Okay. So before proceeding to uniform convergence, you have to first find the pointwise limit. I don't know whether I had done the pointwise limit of x to the power n or not. I don't remember. I had done. I haven't done. Nope. Okay. So let me do the point. Achha, can you tell me what is the pointwise limit? Achha, I'll wait for your answer. What is the pointwise limit for this function? Okay. I'll do it. I'll be very quick. If x equals to 0, what is the sequence of function? Fn at 0, I have become mad. I should add fn here, no? Fnx. Why fxn? So sorry. This is fnx. Okay. So what is this? What is the sequence? Be quick. What is fn at 0? What are the sequences at 0? This is f1 is 0, f2 is 0, and so on, right? Which converges to 0. Which converges to 0. Let's do it for 1 also. If x equals to 1, what is the sequence of function? This will be 1 comma 1, very good, 1 dot 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 up to 1, which converges to 1. Okay, now if x is any number lying between 0 and 1, I have done for 0, I have done for 1. I have to do this when x is any number lying between 0 and 1. So fn of x is nothing but x to the power n. This is what a geometric sequence. This is a geometric sequence where this is less than 1. This is this being a geometric sequence xn where 0 less than x less than 1 converges to 0. You remember, limit a to the power n tends to infinity. This is 0 whenever a is greater than 0 less than 1. Or remember, this result you have done in sequences. So just use that, and I'm just using that, I'll get 0. So what is the pointwise limit? What is the pointwise limit? Therefore fx, which is limit n tends to infinity fnx, this is nothing but at all the points it is 0 except 1. So 0, if 0 less than x less than 1, even at 0 it is 0, and 1 if x equals to 1. So this is the pointwise limit. Did you understand or no? And you may copy this down, be quick. So therefore f of fnx converges pointwise to f on 0 1. Okay, so I have proved this, that this sequence of function converges pointwise to the function f defined by that 0 if 0 less or equals to x less than 1, and 1 at x equals to 1. Okay, now come to the part of uniform convergence. So what I have to prove that this function is uniformly convergent on 0 to k, where k is strictly less than 1. So let's start by that. So firstly, we will take epsilon positive. So let epsilon greater than 0. For 0 less than x less than 1. That means I am choosing points from this sub-interval or this interval. This is strictly less than 1. So point here will be strictly less than 1. Right? Suppose k is 0.9. So you can clearly say that 0 less than x less than equals to 0.9, which is strictly less than 1. So in general, point here, any point lying in this interval will be strictly less than 1, just because k is strictly less than 1. Right? So I am choosing a point in that subinterval. So I have to start from here, right? I have to find that n. So fn x minus fx. Let's find this. I want to check that for what values of n this will be less than epsilon. So I'm starting from here. What is this? F of xn is x to the power n, right? Minus fx. Fx at all of these points will be always 0, because 1 I am not considering. Did you understand why fx is 0 in this interval? Because fx is 1 only at 1. So 1 is not here. So at any other point it will be 0. So this is nothing but modulus of xn. But xn's are already positive just because x is positive. So this will become x to the power n. Yes or no? So I am taking epsilon greater than 0 and I am choosing any point from that subinterval, calling that point as x. I want to see that when is this less than epsilon. So this is less than epsilon if x to the power n is less than epsilon. Yes or no? Clear? Very simple up to here.
Yes, sir.
Okay. Now my question is, how will you find n from here? Can you tell me how can I find n from here? That means what Rajkamal is saying, we can take log both sides. So if we take log both sides, what will happen according to Rajkamal? I am not saying. Then n log x less than log epsilon. Yes or no? Yes or no?
Yes, sir.
Actually, no. This line is wrong. Who can justify me why? This is wrong. This is wrong. Who will tell me why? Okay, this is the graph of log x that I have plotted. You see here, between 0 and 1, log x is always negative. Right? Between 0 and 1, log x is always negative. This is one thing that you should take care of. After 1, the graph is going up. That means log x is positive after 1. But before 1, log x is always negative. Right? So you see, yes, very good. So if I am taking log, the inequality will change because this number is less than 1. So this is the reason I will not take log directly. What I will do, I will reciprocate both sides first. If I am reciprocating, I will get this. Now, why I am reciprocating? Because when x is greater than 0 and less than 1, 1 by x will now become more than 1. You see, x is less than 1 and that implies 1 by x is more than 1. So now what Rajkamal says, taking log will not hamper anything. right? So this can be written like this: 1 by x whole to the power n 1 by epsilon. So n log 1 by x greater than log 1 by epsilon. Yes or no? Because now this is a number more than 1. This is the reason I am doing this. For number more than 1, log x is positive, so the inequality remains. If you are taking log here, you have to change the inequality just because this is less than 1. So log will be negative. So did you understand why I am doing this way, the other way, not directly?
So,
Okay, so this implies n greater than log 1 by epsilon by log 1 by x. Why I can divide? Because and the inequality remains same, because this is a positive number, since log 1 by x is a positive number greater than 0, because 1 by x is positive. Okay, because 1 by x is positive. Not only positive, it is more than 1, as 1 by x is more than 1, so the log value will be positive, so you can divide and the inequality remains same. Okay, now look at this interval. The interval that I am taking care of is 0 to k. The interval is 0 to k. So in this interval, so you see, just try to understand my point. Now x greater than 0 less or equals to k, for this one, one by x will still be greater than 0, or I can just simply say 1. I'll not consider this, leave it. From here only you see, the number log 1 by epsilon by, sorry, this was x. The number log 1 by x, no, did I make a mistake? Oof. This was epsilon only, this was x. This is 1 by epsilon. So many katakutis. So this is what? N greater than, I'll write it again, log 1 by epsilon by log 1 by x. You copy this down up to here, and then I'll again explain. And what to do next, I'll tell you. This number log 1 by epsilon by log 1 by x, this number increases with x having maximum value log 1 by epsilon by log 1 by k on 0 up to k. Who can justify me with this line? Why this has maximum value log 1 by epsilon by log 1 by k on this one? Can you tell me why this value is maximum? Use some inequalities. So think, okay, why this has maximum value? This on this interval, just use some inequalities that x less greater than 0 and less or equals to k, and try to get the inequalities. Now you see, if I choose n, because this is the highest value, this is the greatest value, maximum value. If I choose n just more than this inequality will hold for whatever x that I am choosing, right? So I know the maximum value of n that can be that can be achieved will be this, which will be more than this. So any integer more than this will work. So what I'll do, choose m equals to box of this function that becomes an integer and take one more than that. So plus 1. Are you getting my point? Because this may not be integer. First I'll convert that to integer. This will be less than this. If I add 1, this will still remain an integer. So choose m this which belongs to natural numbers. Okay, which belongs to natural number. Getting my point? So the inequality, I started from here. So this is less than epsilon for any x between this. Hold for this m. So what I'll write? So therefore, modulus of fn x minus modulus of x is less than epsilon for all n greater or equals to m and 0 less than x less than 0 less than x less than 1. Okay. Also, I did not consider 0 here. Right? So I have to take 0 also. Also, at x equals to 0, modulus of fn x minus fx, both being 0, 0 minus 0 is always less than epsilon for all n. So combining these two, what can I say? Therefore, fn x minus fx is less than epsilon for all n greater or equals to m. This is working for every n more than 1. This will also work for this then, no? N greater or equals to n, and for all x belonging to 0k. Therefore, fn converges to f uniformly, or another way of writing this is fn, this with 2 arrows, on 0k, on 0k. So if you have confusion in any line, feel free to ask. Just last part is remaining, that at 1 the convergence will not be uniform. So the question was this: prove that it is uniformly convergent on 0k but not uniformly convergent on 0. So the last part, I will be very quick. Last part is very simple. So when x approaches 1, so I'm talking about this subinterval 0 to 1. So when x is approaching from the left hand side towards 1, when x approaches 1 negative, okay, the number log 1 by epsilon by log 1 by x. Look at this number, I'm talking about this number. Log 1 by epsilon by log 1 by x. When x is approaching towards 1, so this is becoming log 1, right? It's getting very close and close to log 1. So what is log 1? It is 0. Right? So when x is approaching towards 1, this number is tending towards infinity because denominator is getting very big. Are you getting my point? Sorry, very small, because x is approaching 1, so this number is tending towards 1. So this log will become very close to 0, so this is going to infinity. Again I'll repeat, you see, when x is approaching 1, this number is getting smaller and smaller because you know the log 1 is 0. So it is getting very close to 1 and log 1 is 0. So this number as a whole is going towards infinity. Got it? So you see, Thus, it is not possible to find a positive integer n or find m belonging to natural number such that modulus of fn x minus fx is less than epsilon for all n greater or equals to m and x belonging to 0 1. The problem lies at 1. The problem lies at 1. Okay, hence fn does not I should not write like this, does not converge uniformly to f on 0 1. So you see, if I give you K as 3 by 4, 5 by 7, this sequence of function is uniformly convergent on that subinterval, but at 1 there is a problem. So it is not convergent on not uniformly convergent on 0 1, but that is definitely uniformly convergent on any subinterval of this one, proper subinterval of this one. So this completes the proof. If you have any confusion, please ask.